Classification with the Melin dataset. In this lesson, we will learn to approach a binary classification problem using the Melin dataset. Classification helps us separate data into categories. It is important in many real-world problems, such as predicting whether an email is spam or not. Melin is a challenging synthetic dataset designed to test feature selection and machine learning techniques. By the end, you will understand how to work with high-dimensional data, build models, debug, and follow best practices. You will also see an end-to-end workflow, from loading the data to making predictions. Running the cell now. We import NumPy for numerical computations. We import pandas for handling datasets. We import matplotlib for visualizations. We use fetch_opml to get the Melin dataset from OpenML. We import train_test_split to split our data into training and testing sets. We use random forest classifier, a robust model for handling many features. We import classification_report, confusion_matrix, and accuracy_score for evaluating models. We use standard scaler to standardize the features for better model performance. We import warnings to control warnings in the notebook. We ignore warning messages for cleaner output. Running the cell now. Practice. Can you recall why we use standard scaler before modeling data, especially with many features? Understanding the Melin dataset. The Melin dataset is a synthetic, difficult classification problem. It contains 2,600 examples, each with 500 numeric features. There are no missing values, and no categorical features. The target is a class, which can be 1 or 2, this is a binary classification. The classes are balanced, with equal numbers of each class. A common beginner mistake is ignoring the high feature count, which can lead to overfitting. Another mistake is skipping data exploration and preprocessing, which makes model building harder. Running the cell now. We set the seed to 42 for reproducible results. We fetch the Melin dataset from OpenML. It downloads automatically. We extract the feature data into variable X. We extract the target labels into variable Y. We print out the shape to see how many samples and features we have. We print some of the first few feature names. We see which target values exist. Running the cell now. This output confirms that the Melin dataset has 2,600 samples and 500 numeric features, matching the lesson's description. The displayed feature columns, V1 to V5, illustrate the standardized naming scheme without categorical variables, and the target values show the binary classes 1 and 2, verifying the balanced classification task. This check ensures we correctly loaded the data with expected shape and labels before proceeding with analysis. Beginner tip: always check your data dimensions before proceeding. We look at information about the features, data types and presence of missing values. We look at the distribution of the target variable to confirm class balance. Running the cell now. This output confirms the Melin dataset structure, showing 2,600 examples with 500 numeric features, V1 to V500, as expected for a high-dimensional problem. The target variable's class is perfectly balanced, with 1,300 samples in each class, which is crucial for fair binary classification. This verifies the dataset's properties before proceeding with any modeling steps. Try: how would you check for missing values? Why is class balance important in classification? We take a quick look at 5 random rows of the data to see sample feature values. Print the first few rows of the sample data to display these examples. Running the cell now. Here, we randomly sampled 5 examples from the Melin dataset to get a quick look at the feature space. Notice each row corresponds to an example with 500 numeric features named V1 through V500, illustrating the high dimensionality we will work with. This output confirms there are no missing values and every feature is numeric, which sets the stage for the classification challenges ahead. Often, seeing a few data points helps us understand what kind of values we are dealing with. We calculate the mean for the first 10 features. We calculate the standard deviation for the first 10 features. We display the means. We display the standard deviations. Running the cell now. This output shows the means and standard deviations of the first 10 features in the Melin dataset, highlighting the variability in scale across features. Notice how some features have much higher variation, e.g., feature 5 with STD-41, while others are more tightly clustered, e.g., feature 8 with STD-1.4. This insight is crucial for understanding feature distributions and may guide pre-processing steps such as scaling before model training. Practice: why do you think standardization might help data like this? We convert the target labels to integers for easier plotting. We create a small figure for the class histogram. We plot the distribution of both classes. We add a title for clarity. We label the x-axis. We label the y-axis. We adjust layout for better appearance. We display the plot. Running the cell now. This histogram shows the class distribution in the Melin dataset, confirming that both classes, 1 and 2, have roughly equal counts. Noticing this balance is important because it means we don't need to apply special techniques for imbalanced data during classification. This visualization directly supports our understanding of the dataset's target variable before modeling. Visualizing class balance lets us check if the prediction task is fair for both classes. We split the data into training and test sets with train_test_split. We specify 20% of the data for testing, stratify by Y to maintain class distribution, and set a random state for reproducibility. This closes the train_test_split function call. We print the shape of the training data to verify its size. We print the shape of the test data to verify its size. Running the cell now. This output confirms the train test split of the Melin dataset, showing 2080 training samples and 520 testing samples, each with 500 features. Notice that the split respects the dataset structure and maintains the feature dimensionality, which is crucial for consistent model training and evaluation. This step ensures we keep the data balanced and representative for the binary classification task ahead. Stratification is important with balanced classes to keep both sets representative. We initialize a standard scaler. We fit the scaler on the training data and transform it. We use the same scaler to transform the test data. We print the shape to confirm nothing changed except the scaling. Running the cell now. This output shows the shape of the scaled training data after applying standard scaler. Notice it retains the original 500 features but now has 2080 examples, confirming the pre-processing step preserved the dataset structure while standardizing feature values. This scaling is crucial for many machine learning models to perform effectively on the Melin dataset. Always fit scaling objects only on training data to prevent information leakage. We create a random forest classifier with 100 trees. We train the model on the scaled training data. We make predictions with the trained model on the test set. We print overall accuracy of the model. Running the cell now. This output shows the classification accuracy of a random forest model on the Melin dataset test set, achieving about 68.5% accuracy. Notice that despite the large feature space and balanced classes, the accuracy is moderate, highlighting the dataset's complexity and the challenge of distinguishing its classes. This fits the lesson's focus on understanding the difficulty of Melin and how a robust model like random forest performs on it. Beginner tip: random forests handle high dimensions fairly well, but can still overfit. We print the confusion matrix to see correct and incorrect predictions per class. We print a full classification report for precision, recall, and F1 score. Running the cell now. The confusion matrix shows that our model fairly evenly classified examples from both classes, with about 68% accuracy overall. Notice the balanced counts in support, 260 each, reflecting the dataset's equal class distribution, and similar precision and recall scores around 0.68 to 0.69 for both classes. This output highlights the model's moderate performance on this challenging Melin dataset, emphasizing the difficulty of accurate classification despite balanced data. Intermediate, notice if either class is harder to predict. Which metric is most important here? We extract the feature importances calculated by the random forest. We find indices of the 10 most important features. We make a horizontal bar chart to visualize them. We plot the bars with their feature labels. We label the x-axis for clarity. We title the chart. We show the plot. Running the cell now. This bar chart highlights the top 10 most important features from the Melin dataset as identified by the classifier. Notice how only a small subset of the 500 features carry significant predictive power, reflecting the challenge of distinguishing signal from noise. This visualization helps us focus feature selection and understand which inputs most influence the binary classification. Intermediate, feature selection helps reduce noise and overfitting in high-dimensional data. We will remove the least informative features and keep only the top 20. We select columns by their importance ranking. We prepare training data using these columns. We prepare test data the same way. We initialize a new scaler for this reduced dataset. We fit and scale the training data. We scale the test data. We set up a new classifier. We fit the model on the reduced data. We predict using the test set features. We print the accuracy using only 20 features. Running the cell now. This output shows that using only the top 20 most important features, selected by the model, still achieves a high accuracy of about 88.7%. Notice how this reduced feature set simplifies the data from 500 to 20 dimensions while maintaining strong predictive performance, highlighting how feature selection can improve model efficiency without sacrificing much accuracy. This reinforces the intent to identify and focus on the most informative variables in the Melin dataset for effective classification. Intermediate, less can be more. Does performance improve or decline with fewer features? We try logistic regression for comparison, suitable for binary tasks. We increase the maximum iterations to ensure convergence. We fit the model on scaled training data. We make predictions on test data. We print the accuracy score for logistic regression. Running the cell now. This output shows the accuracy of a logistic regression model on the Melin dataset test set, scoring about 54.6%. Notice that this accuracy is only slightly better than random guessing, 50%, highlighting the challenge of this synthetic dataset and the difficulty in separating the classes with a basic linear model. This underscores the need for more advanced techniques or feature engineering to improve classification performance on Melin. Comparing models helps us check whether our random forest is the best choice. We import PCA for dimensionality reduction. We set up PCA to extract two principal components. We fit and transform the training data to 2D. We create a square figure for clarity. We plot the first two components and color by target class. We label first axis. We label second axis. We title the plot. We display the projection. Running the cell now. This PCA plot shows the trained data projected onto its first two principal components, summarizing the original 500 features into two key dimensions. Notice how the points, colored by class, overlap significantly, highlighting the dataset's complexity and difficulty in separating classes. This visualization helps us understand the data structure and confirms why advanced methods are needed for this challenging classification task. Advanced, unsupervised projections like PCA help visualize whether classes are separable. We try an advanced model, support vector classifier, on the top 20 features. We import SVC. We create an SVC with a radial basis kernel. We fit to our reduced, scaled train data. We predict on the test set. We print the accuracy for SVC on the top features. Running the cell now. Here, the SVC classifier trained on the top 20 scaled features achieves an accuracy of around 86.5%, highlighting its effectiveness on this challenging dataset even with a reduced feature set. This output demonstrates that careful feature selection combined with a robust classifier like SVC can yield strong performance on the Melin dataset's balanced binary classes. Does a kernel method outperform tree-based and linear models on this data? We comment that this is an advanced pipeline using feature selection and cross-validation. We import the cross_val_score function for cross-validation scoring. We import select from model for feature selection based on model importance. We create a select from model instance using the CLF and select features with importance above the median. We apply the feature selector to x_train_scaled and y_train to obtain the reduced feature set. We evaluate a random forest classifier with 100 trees using 5-fold cross-validation on the reduced data. We print the average cross-validation accuracy score. Running the cell now. This output shows the mean cross-validation accuracy after applying feature selection to reduce the Melin dataset's 500 features to the most important ones, using the median importance as a threshold. Notice how the accuracy of about 71% reflects the model's performance on a smaller, more relevant feature set, demonstrating that careful feature selection can improve or maintain classification effectiveness while simplifying the data set. This confirms the intent of using feature selection within the pipeline to enhance model generalization on this challenging dataset. Advanced cross-validation gives a more stable idea of model performance by averaging over several splits. We want to see what happens if we input data with the wrong number of features. We use a try-except block to handle errors. We generate random data with 300 features instead of 500. We try predicting with the model, which expects 500 features. If an error occurs, we print it out. Running the cell now. This error message clearly shows that the input data must match the expected shape, in this case, 500 features per example. The model, trained on the Melin dataset with 500 features, cannot handle data with fewer features, which helps emphasize the importance of consistent input dimensions for prediction. This reinforces the lesson on understanding the dataset structure before applying a classifier. Practice, error messages are your friends when diagnosing problems in data pipelines. We check for overfitting by comparing model accuracy on train and test sets. We calculate accuracy on the training set. We calculate accuracy on the test set. We print the train accuracy. We print the test accuracy. Running the cell now. This output shows a classic sign of overfitting. The random forest achieves perfect accuracy on the training data but significantly lower accuracy on the test set. This means the model learned the training examples too specifically and failed to generalize well to new, unseen data. Recognizing this helps us understand the need for regularization or simpler models with the complex Melin dataset. Best practice: if there is large difference between train and test accuracy, your model might be overfitting. A best practice is to export only relevant features for reuse. We extract the names of our top 20 features. We select those features from the trained set. We save as a CSV file. We confirm the CSV has been saved. Running the cell now. This output confirms that the code successfully saved the top 20 selected features from the Melin dataset into a CSV file. Notice that by reducing the dataset to these key features, we streamline further analysis and modeling, focusing on the most informative variables for this challenging classification task. This step is essential for improving efficiency and interpretability in handling high-dimensional data. Now opening the exported CSV file so we can explore the top 20 features visually. Try opening this CSV and exploring the feature columns in Excel or another tool. It is a common best practice to wrap preprocessing and modeling in a pipeline. We import the pipeline class from scikit-learn.pipeline to create pipelines. We start creating a pipeline object with a list of steps. We add a scaling step using standard scaler to the pipeline for feature normalization. We add a random forest classifier with 100 trees and a fixed random state to the pipeline. We fit the entire pipeline, including scaling and model training, on the training data. We evaluate the pipeline's accuracy on the test dataset and print the result. Running the cell now. This output shows the test accuracy of a pipeline combining standard scaling and a random forest classifier on the Melin dataset. The accuracy of about 68.5% reflects the model's ability to distinguish between the two balanced classes based on the 500 numeric features. This demonstrates a common and reproducible approach to preprocessing and classification, highlighting the baseline performance on this challenging synthetic dataset. Pipeline objects keep all steps in one place to avoid mistakes and make experiments reproducible. Let us simulate predicting classes for new data points. We select a few rows from the test data. We scale them using the previously fitted scaler. We use the trained classifier to predict their classes. We print out the predicted classes. Running the cell now. Here, the model predicts the classes for 3 new, unseen samples from the test set. Notice the output array shows predicted class labels, illustrating how the trained classifier generalizes to new data. This confirms the intent of this step, to perform end-to-end prediction on fresh inputs using the fitted scaler and model. Recap: you have loaded, explored, modeled, and made predictions with a complex dataset in just a few lines. Lesson recap and YouTube call to action. You have covered loading and exploring high-dimensional data with Melin. You practiced classification, feature selection, model evaluation, and error handling. You built robust pipelines and saw real issues with feature selection and overfitting. Try building your own end-to-end workflow for a different dataset, or experiment further with Melin. If you found this helpful, please subscribe and share our channel for more machine learning lessons. Like and comment with your questions or projects, we are here to help you learn. Running the cell now.